So this is our research topic, the Petronas Twin Tower in Malaysia. And we are Bill, Anthony, Ren, Christine, and Emily.
So first, I would like to talk about why we choose the Petronas Twin Towers. The term Twin Towers in architecture refers to two tall structures with nearly identical characteristics and similar height, usually constructed close to each other and a part of a single complex. It is a relatively special structure, and the Petronas Twin Towers in Malaysia, among all twin towers, have a unique position. The Petronas Towers, with a height of 451.9 meters, are the world's tallest twin towers. The sky bridge, with a length of 58.4 meters, connects the two towers and is one of the most attractive features of the towers. When we are searching for the literature related to the Petronas Towers, we realize that previous studies on the Petronas Towers mainly focus on the analysis of the structural parts and the tower and the materials used to construct the tower and its foundation. However, the response of the towers to loads at different frequencies is rarely studied. So we would like to study the model and harmonic responses of the Petronas Twin Towers at different frequencies, which will provide an insight into the tower's response to various environmental situations it's exposed to in Malaysia. Next slide, please.
So now I'll talk about the objective of our study. The objective of our research is to construct a finite element model to analyze the maximum normalized deformation at different frequencies for the Petronas Twin Towers. We also aim to analyze the building's deformation under pressure with different damping ratio. We use 3 different damping ratios to study the effect of the tower's dampers on the building. Next slide, please. And so here's more on the background of the building. The Petronas Twin Towers was designed by Cesar Pelli, an Argentine-American architect. And the towers were designed to resemble an 8-pointed star that represents unity, harmony, stability, and rationality in Islamic cultures. So this building represents the cultures in Malaysia and has special meaning to Malaysia as a result. The construction of the Petronas Towers started on March 1st, 1993, and was completed in 1996. They were officially opened on August 31st, 1999, and the 2 towers each have 88 floors. Each tower weighs 300,000 tons, so the total weight is 600,000 tons. Towers were made of high-strength concrete with various strengths up to 80 MPa. The foundation of the towers is a 4.42 meter thick concrete mat, and it is supported on 104 concrete friction piles. Next slide, please.
One of the features of this building is its sky bridge. The sky bridge is an essential component of the Petronas Twin Towers because it connects them to facilitate movement between the 2 towers. And the sky bridge is 58.4 meters long and weighs about 750 tons. And it is a double-decked sky bridge, which is located at levels 41 and 42, which is about 170 meters above the ground. And the structure of the sky bridge is constructed of structural steel, and there is a rotational pin in the center of the main bridge girder, which can let the arc crown rise and fall when the towers move closer or further apart. Next slide.
And so here's the dimensions of the towers. To find the most accurate dimensions, we found the construction drawings published by the designer of the building. So here are some pictures of the different bases of towers, and then on the right is a picture of the entire tower and its height broken into different parts. Next slide, please. And so here's the specific dimensions for floors 1 to 59. The total height is 247.5 meters with a base width of 55.508 meters. And for floors 60 to 72, the total height is 53.3 meters with a base width of 51.255 meters. For floors 73 to 81, the total height is 36.9 with a base width of 45.608 meters. And for the bustle, it is 24.0 meters in diameter. And the pinnacle has a height of 73.575 meters. And for each floors, the floor has a height of 4.0 meters. And for the sky bridge, it has a span of 58.44 meters with a height of 9.45 meters. That is about a little bit more than 2 floors in total. And it has a width of 5.29 meters. And for the legs that support the sky bridge, they are 42.6 meters now long and 1.1 meters in diameter. Next slide, please. And so for the materials of the building, it consists of concrete with various strengths, as you can see with the picture on the right. So the bottom of the tower consists of concrete strength of 80 MPa, which is the strongest out of all the concrete used to build this building. And then from floors 23 to 26 to 60, the columns has a concrete strength of 60. And then from floors 61 to 84, it's grade 40 concrete used to construct the columns. And for the core of the building, it's grade 80 concrete up to floor 14, and then from floors 15 to 44, grade 60 concrete was used, and from floors 45 to 84, grade 40 concrete was used. And the foundation of the building was grade 60 concrete as well. Next slide, please.
Okay, now I think that it's my part to show you guys about our construction of the geometric model. Well, because we think that the structure of the Petronas Tower is a bit complex, so we decided to model step by step by starting with a very simple and easier role model and gradually advance to a more accurate and detailed structural model. In the whole modeling process, we modeled 3 models: the raw model, the hollow model, and the structural model. And we start with a solid raw model, and then we modeled a hollow model. And as its name said, it has a hollow hole in the center of the model. And finally, we made a structural model of the tower, which only contains the basic bearing structures and the dampers on the top of the tower. Next page, please. And now is how we model our role model. And when we model our role model, we haven't got many precise drawing of the Petronas Tower. So what we can do is just to find a clear image which shows the proportion of each part of the tower. Then we use the calculation to get the height and the diameter of each part of the tower, and then we model it as these parameters. And for the sky bridge, we just use a solid block in the middle of the tower, which has the same length and the same height above the ground with the real bridge to represent the sky bridge. And also we add a 40-meter deep foundation at the bottom of the tower, at the bottom of the model. Next page, please. And as you can see, the picture on the left is the drawing that we use to calculate the basic parameters of the tower. And the model on the bottom is the raw model. And as you can see, it's really just a very simple and basic model, which just has some basic features of the Petronas tower. Okay, next page. And now comes to our construction of the hollow model. And after we made a raw model, because the raw model did not very similar to the real tower, then we decided to improve the model. So we found some drawings that shows the parameters of the base of the tower and the height of the tower. So we modeled the hollow model, which has a similar geometry shape with the real tower and some very similar structural features about the real tower. And we also found some other drawing which shows the structure of the sky bridge. We also use them to help us model the sky bridge. Next page, please. These are the drawings that we use to get the basic parameters of the length and the size of the base. And the drawing on the left shows the diameter of the level 1 and level 2. The level 1, I think that it should be the ground level to level 55, and the level 2 should be about level 56 to around level 70. And the drawing on the right is the parameter of level 3, which is which I think should be level 73 to about level 80. Okay, next page, please. And these are also some drawings showing the height of the tower and the parameters of the pinnacle. Next page, please. Okay, now here comes our model of the hollow model, and the model on the left is a more general look about our whole hollow model, and the model on the right is a more detailed look about the sky bridge and the tower itself. Well, most of our structural analysis are done on the hollow model because it has a similar structure and geometry features with the real Petronas tower, and the answers can successfully create grids on this model. Next page, please. Now comes our final part of our model construction, the construction of the structural model. And this because at the period we finish our modeling of the hollow model, we still think that the hollow model lack of some of these structural features. So we start to model our structural model with the help of our TA Zoshua in order to get the best structural accuracy. To make this model, we refer to some of the drawings to get the arrangement of the supporting pillars. And we also discovered that the hole that we modeled in the hollow model is actually a supporting wall in the middle of the tower. So, and we also modeled it in our structural model. We also found that the different levels actually have different heights. So we also set different height values for different levels. Okay, next slide, please. And the drawing on the left is the arrangement of the supporting pillars of each level. As you can see, there are 16 pillars arranged in circle around the whole base. And the drawing on the right is the structure drawing about the sky bridge. And as you can see, there are 10 supporting pillars on the sky bridge, and the sky bridge has 2 supporting legs beneath it. Next page, please. So this is our final model of our structural model. Just like the hollow one, the picture on the left is a more general look, and the picture on the right is a more detailed look. Well, unfortunately, we have found that the student version of ANSYS failed to create grids on our structural model. we think that it may be because the structural model has too much elements and the student version of ANSYS failed to separate these elements. Okay, now I'm going to hand over to Bill for our final part, the results and the conclusions.
Okay, so I'm gonna talk about the settings of our ANSYS model. So according to the Asia Wind Energy Association, the average wind speed in the Kuala Lumpur area is 1.8 meter per second. And the tower's optimistic design wind speed is 35 meters per second. And since the steel's material characteristic tends to be lighter, so it cannot meet the comfort and safety requirement in the area. So eventually the engineers selected reinforced concrete as the main material of the tower, which meet the comfort and design requirement with its large mass and high rigidity. And moreover, it can also damp the tower's sway during strong wind weather and minimize its vibration. And another reason to use the concrete instead of steel is that Malaysia itself doesn't produce structural steel, and importing the steel will increase the cost. So therefore, the reinforced concrete structure for the Twin Tower is the most suitable way for the existing conditions. And on the other hand, Malaysia is not in an earthquake zone, so the tower is mainly designed for wind resistance. So it was designed wider at the bottom and narrower at the top. And at the top of the tower, you can see at the bottom picture, is the damper of the Twin Towers, which can control the counterweight objects to move in the opposite direction through spring and hydraulic device in strong wind weather or earthquake, thereby reducing the vibration of the building. And this is our boundary condition we adopted. So in the analysis, since the tower were in contact with the ground, so the tower was subject to the boundary condition at the bottom of the model. So as you can see. And we also conduct a mesh independent study to ensure the accuracy of our result. The study also, so to make sure the results dependence on mesh density, we change the mesh size and we test the relationship between the number of nodes and the fundamental frequency. And this is our graph. So as you can see, there's no major discrepancy in the result. So the mesh independent study shows the result is independent of mesh density. However, in our ANSYS analysis, which I just used the one with more nodes because it wasn't taking too much time to generate the result. And this is the meshing of our ANSYS model. I believe this is about 20,000 nodes. And this is the material we adopted, as Christine mentioned. So there are mainly 3 types of concrete and structural steel at the top of the tower and the sky bridge. So as you can see, as the grade increase, the density of the concrete increase, and also Young's modulus and Poisson's ratio. So here is our model analysis. So this is at a frequency of 0.2568 hertz, and at that time, the maximum normalized deformation is 5.1971 times 10 to the negative 5 meter, and it is a x direction displacement and z-axis torsion. And this is mode 2 at frequency of 0.31777 hertz. The maximum normalized deformation is 5.2416. times e to the times 10 to the negative 5. And it is a z direction displacement and x-axis torsion. And this is a mode 3 at frequency 0.36427 hertz. And this is the normalized deformation. And this is a y direction torsion and z-axis non-sway frame motion. And this is at a frequency of 0.65195 hertz. And this is our maximum normalized deformation. And this mode is a x-axis non-sway motion. And this is mode 5, which is at frequency of 1.2379 hertz. And the maximum normalized deformation is 0.00014622. And this is a z-axis sway or buckling. And this is the last mode, which is at a frequency of 1.2442 hertz. And the maximum normalized deformation is 0.0013222 meter. And this is a x-axis sway or buckling. And this is our harmonic response. So this is at a 0 damping ratio, and 0 damping ratio means there may cause a large peak harmonic response around the natural frequency due to resonance, and this is what our research topic mainly about. So as you can see, this is the frequency response diagram, and this is the phase response diagram. And the result of the 0 damping ratio is quite significant. So the maximum amplitude is at 61.607 meter, which can produce very large energy compared to the rest I will show later. And the phase angle is at 180. And this is the minimum and the maximum pressure applied. As you can see, the maximum is at the bottom of the tower, and maximum and the minimum is at the top of the tower. And this is our result for the 0.01 damping ratio. So the result, so the maximum amplitude actually decreased a lot, but and it is 0.154 meter. And the phase angle is now 90.577. And these are where the minimum and maximum pressure applied is. I think it's pretty much the same place. And lastly is the 0.02 damping ratio. So the maximum amplitude is decreased a lot. And the phase angle is now 90.007. And these are the maximum and minimum pressure applied on the tower. And these are the 3 damping ratio comparison. As you can see, maybe the animation doesn't play too much, but it is pretty significant. So the damping ratio actually plays a significant role in harmonic responses. And there's nearly like a 200% difference between 0 damping ratio and 0.01 damping ratio. So larger the amplitude, larger the energy. Therefore, dampers are really vital to tower safety and comfort. These are the deformation of the Twin Tower under equivalent stress. So I will hand it over to Christine.
And so in conclusion, So we performed model analysis and harmonic response analysis of the Petronas Twin Towers. For model analysis, we use 6 different natural frequencies ranging from 0.2568 Hertz to 1.2442 Hertz as presented by Bill. And the maximum normalized deformation and displacement of the towers were analyzed. And for the harmonic response analysis at a pressure of 735 Pascal with 3 different damping ratios, 0.0, 0.01, and 0.02 were performed to determine the building's frequency response and phase response. And results of the harmonic response analysis show that the dampers placed at the towers were indeed significant for the safety of the towers.
And thank you. That's all for our presentation.
Very nice. I was impressed, very impressive. Any questions from the audience? I didn't realize the bridge has such a profound impact on the response of the twin structures. It created anti-symmetry, right? One tower moving forward, the other tower moving backward. So that is an additional mode of vibration. That would not be there if there was no bridge between the tower. In fact, the first mode is forward mode, right? Perpendicular to the bridge. And then the second mode is parallel to the bridge, which is left and right mode. So that is a separate mode of vibration created by the presence of the bridge. I have a question about the hollow structure. Am I correct that the hollow portion of the structure is rectangular in cross-section? Is that what I saw from your slides?
Pardon, Professor, I'm not very clear about what you mean about the hollow structure is rectangular.
The hollow portion, the void, the empty portion of the structure inside. Is that what you mean by a hollow structure?
Actually, I think that the reason why I named the second model the hollow model is because we have a rectangular hole on the center of the structure.
That is what I meant. That the square or rectangular void inside the structure, that is the hollow portion, right?
Yes.
So the vibration analysis that you conducted, was that based on the hollow structure or the solid structure?
That is based on the hollow structure.
The hollow structure. The third one, the most refined one, you didn't pursue because you ran out of memory space, right? In ANSYS. Yeah. Okay, so that's understandable. Let's see. Was there any difference between the hollow structure and the solid structure? Did you make a comparison between the two responses?
No, but in the first presentation we gave last week, I think that one is a solid structure, and I don't think there's much of a difference in terms of deformation.
Did you look up in the literature to find out if there was any reported vibration property of the real Petronas tower?
The vibration property, I mean,
like the first mode, the fundamental frequency, is it really 0.25 hertz? Is it close to that?
I think it's pretty close. I don't remember right now.
Mhm. No, I was just curious. I don't know the answer. I was just curious to find out if there's any recorded or measurement of the or calculations of the fundamental frequency of the tower. Probably not, huh? Okay, any other questions from the audience? If there are no questions, then I am going to stop the recording and then we'll take a 5-minute break. When we come back, we'll hear it from the Parthenon group.